After being closed for a long time, the switch S in the circuit shown is thrown open at time t equals 0 seconds. In the circuit, the EMF of the battery is 24 volts, resistor A has a 4 kilo ohm resistance, and resistor B has a 7 kilo ohm resistance. The inductance of the inductor is 589 millihenry. In the first part of the problem, you need to find the EMF across the inductor immediately after the switch is opened, and in the second part, you need to find the time at which the current in resistor A has a magnitude of 1 milliamp. Let's write down what the problem gives us first. We have the EMF of the battery as 24 volts, the resistance of resistor A of 4 kilo ohms and the resistance of resistor B 7 kilo ohms, and the inductance of the inductor 589 millihenry. We need to find the EMF across the inductor immediately after the switch is opened. Well, when the switch is open, the battery is taken out of the circuit, and the inductor behaves like a battery for the rest of the circuit now. As you can see, the rest of the circuit is made up of these two resistors, which are connected in series and in series with the inductor. That means that the voltage provided by the inductor for the two resistors is calculated as the current multiplied by the equivalent resistance of the circuit. This equivalent resistance is nothing else than the sum of the two resistances, and if you add 4 and 7 kilo ohms together, you get that the equivalent resistance for the circuit is 11 kilo ohms. This is for the case where the switch is open, don't forget that. Now, the second question is, what is the current that the inductor provides? Because we need to know both the equivalent resistance and the current. Well, the current that the inductor provides at the first moment when the switch is open has to be the same current. Remember, the inductor opposes the change in current. The same current as the one that the inductor had going through it just before the switch was open. Now, when the switch is closed, remember, after a long time, the inductor behaves like a wire, which means that the same current that goes through resistor A is going through the inductor L when the switch is closed. If I can find the current through resistor A with the switch closed, I know what the current through the inductor is going to be. Well, if you look at the circuit when the switch is closed, resistor A and resistor B are connected in parallel and across the battery. Therefore, we can easily calculate the current through resistor A as the voltage across the resistor, which is nothing else than the EMF of the battery, divided by the resistance A. The EMF is 24 volts and the resistor is 4 kilo ohms or 4000 ohms. And the current is 6 times 10 to minus 3 amps or 6 milliamps. Now we can easily calculate the voltage through the inductor as the current 6 times 10 to minus 3 amps multiplied by the equivalent resistance of the two resistors in series, which is 11 kilo ohms. So we write it as 11 times 10 to the third ohms. And we get that the voltage provided by the inductor is 66 volts. I would like you to realize that we have obtained the voltage that the inductor provides that is bigger than the EMF provided by the battery. Now, for the second part of the problem, we need to find the time at which the current in resistor A has a magnitude of 1 milliamp. Well, the current through the circuit changes with time as a maximum value Imax multiplied by e to minus t over tau, where the current now we know that at a certain moment in time is 1 milliamp. The maximum value of the current is the value of the current at time t equals 0, and the t is something that we have just calculated, 6 milliamps. And the time constant for the LR circuit is calculated as the inductance divided by the equivalent resistance of the circuit. The inductance is 589 millihenry and the equivalent resistance is 11 kilo ohms. That gives me a time constant of 5.3 times 10 to minus 5 seconds. All we have to do is replace all these known quantities in the equation for the current and find the time. That is the only unknown. And then I have left both the maximum current and the instantaneous current in milliamps. So I have 1 equals, maximum current is 6, e to the power minus t divided by the tau, the time constant is 5.3 times 10 to minus 5. You can rewrite this equation as 1 over 6 equals e to minus t over 5.3 times 10 to minus 5 and apply a natural log to both sides of the equation. And that gives you on the left side natural log of 1 over 6 equals a natural log of e to a power is nothing else than the power itself. Don't forget the minus sign though, because that is very important. Remember, your answer for time has to be a positive value. And even though you have a minus here, you have to remember the natural log of 1 over 6 is also a negative value. This natural log of 1 over 6 can be written as natural log of 6 to minus power 1, which means that I can rewrite natural log of 1 over 6 as minus natural log of 6 equals minus t over 5.3 times 10 to minus 5. And from there the time is 5.3 times 10 to minus 5 times natural log of 6. Use a calculator and you will get that the time it takes the current to reach a magnitude of 1 milliamp is 9.5 times 10 to minus 5 seconds. I would like you to realize that even though we talk about switches being open for a long time or closed for a long time, all these phenomena are actually taking place on a very, very short time scale.